Hi, my name is Nick Sterzenbach and my ZID is Z5210010. In this video, we're going to be talking about some preliminary results that I received from completing the gravity and orbits simulation from the University of Colorado. To briefly introduce Kepler's laws of planetary motion, we're going to go through the first law. Each planet's orbit around the Sun is an ellipse. The Sun's center is always located at one focus of the orbital ellipse. Kepler's second law, the imaginary line joining a planet and the Sun sweeps equal areas of space during equal time intervals as the planet orbits. And Kepler's third law, the squares of orbital periods of planets are directly proportional to the cubes of the semi-major axes of their orbits. For our first preliminary experiment, we've switched to the Earth-Moon scenario. Now, in this orbit that you can see, the 27 Earth day orbit, as the Moon rotates the Earth in an ellipse, you can see that the Earth does move. It wobbles slightly as the Moon orbits. Now, to go back to our first experiments for the first part of this assignment, first we're going to look at experiment number 1, and we're going to be looking at where the center of mass exists for this particular experiment. So according to NASA, through mathematical equation, the center of mass is very close to the center of the Sun. The center of the mass is described as the balancing point to which a planet and a star orbit around and is always connected with a non-existent line, such as explained in Kepler's second law. Therefore, in question 1, I would expect the center of mass to be located close to the center of the Sun, just where you can see marked in red. Now, moving to experiment number 4. What you can see we've done here is increase the planet mass of Earth to 2.0. So I would expect the center of mass to shift slightly towards the planet that has increased in size. Although with the Sun moving being so small, it's difficult to notice in this simulation. So as you can see with the red dot, the center of mass has shifted slightly right towards the Sun. Now, in experiment number 7, what has happened is the planet mass has been made smaller and the velocity of that planet has been increased. You can see this completely changed the center of mass, as you can expect, and it has changed the shape of the orbit. Kepler's laws of orbital motion indicate that a planet's orbital speed changes depending on how far away it is from the Sun due to gravitational force. This change in ellipse causes the barycenter to shift, to which I would expect the center of mass to be located much closer to the planet in this example, which you can see in the red dot on this example here. How is this experiment different? The Earth and the Sun versus the Earth and the Moon? The Earth's center of mass is different from the Sun. The Earth wobbles as it orbits due to gravitational pull creating a non-uniform ellipse, creating a different center of mass between the Earth and the Moon. Now the Moon orbits around the center of mass, not the center of the Earth. The center of mass being located around 1,100 miles below the Earth's surface according to Science Direct. This is different from the Sun, as we saw in the previous experiment where the center of mass is closer to the center. The mass of the Earth and the Moon compared to the Sun also accounts for shift of barycenter in this unique scenario. Now for our next example, we'll be measuring the distance in astronomical units between a star and a planet in this example. Now, the distance to the Sun from the Earth is 1 AU, or astronomical unit, according to NASA. Using the grid lines as reference to our Sun-Earth simulation, that would mean that the distance of one grid box is 0.5 AU, half of 1 AU. Now, you can see from these examples here, first what I have done is I have reduced the distance to 0.5 AU, which has completed an orbital period of 90 days. And in the second experiment, I've increased the distance to 1.5 AU, which has increased the orbital period to 748 days. Now for our third experiment, what we have done is we increased the planet distance to 2.5 AU, which has increased the orbital period to 1,116 days. For the fourth experiment, we've done something a little bit different. We've gone almost as small as we can to 0.25 AU, which has completed a very small orbital period of 19 days. Now, this does follow Kepler's third law, as we would expect. As the orbital distance gets smaller, the orbital period is less. So as the planet gets further away, the orbit is more. As the planet is closer to the star, it is less. Applying these distances to our own solar system and distances, Based off the previous experiment, the data would indicate that Mercury would have the fastest orbital velocity as the planet is nearest to the Sun, whereas Neptune, due to its distance from the Sun, would have the slowest orbital velocity. The distance from the Sun determines planetary orbit period due to gravitational pull and orbit size. The further away the planet is from the star, the Sun in this case, the further the planet must travel in its orbit, therefore having a larger orbit. This is due to Kepler's third law, implying that orbital periods are directly proportional to the distance or cubes from semi-major axis of their orbit. In these experiments, the Sun maintained the same mass, therefore orbital speed would not be affected due to gravitational pull being maintained. This was a fantastic experiment to gain a more comprehensive understanding of how planet mass, velocity, and gravity can all affect orbit and ellipse differently. I personally gained more understanding of planetary gravitational pull and the different types of ellipse that can be created. The experiment allowed a more visual understanding of Kepler's laws of orbital motion, more specifically the variability in orbit speed as we increase ellipse size and the changes in planetary velocity on its ellipse as the planet distance from the Sun varies, as the gravity and velocity feature allows you to visualize in this simulation. In the Sun-Earth simulation, according to Newton's third law, you would expect the Sun to move during its orbit as it experienced gravitational pull, although the movement is too small to recognize in this simulation. The experiment additionally provoked further research into barycenter and the function of planetary center of mass, and how the varying simulations completed were affected by changing barycenter. Overall, the experiment prompted a more comprehensive and visual style of learning that led to further personal research into astronomical theory and physics and a more detailed understanding of the laws of planetary motion. Thank you.